So here's the plan for basically the rest of the semester, because there's not much left. We're going to do chapter 9 tonight. It's actually, believe it or not that long. And if you had looked at some of the topics, the questions, or the lessons, they were really easy to go through. But we're going to do chapter 9 tonight. Chapter 10 will be next week. You have the week of Thanksgiving off. The week after Thanksgiving, we will do chapter 11. Then the week, so December 7th will be your last test. It'll be the chapter 9 through 11 test. And the final will be the following week. So I'm going to drop chapter 5. I'm not going to go over it. They'll still be in Hawks, so try them. But it's not the end of the world if you don't get those done. As long as you got everything else done, you'll still be over the 80%, which you need to do to get out of taking the final if you're in that boat. You have to have at least 80% of all the topics done. And then plus the 90 and all the tests to not take the final exam. So other than that, the test was decent. 99% of the mistakes that people made were they didn't read the problem correctly. Like the first one, they did it for male instead of female, like little things like that. So the majority of the test actually was very good. All right, the first couple things in chapter 9 we've actually talked about quite often. This is where different books do this in different orders. So like I've actually talked about some of this stuff, not necessarily the exact definitions of the words and stuff. So that's what we're going to go over first. When you're looking at a sample, when you're trying to get a sample, you want a good random sample. So a couple terms that they use is a sampling frame. This is kind of like where you're talking about before we were talking about population. It's just a wording for that. It's identifying everything of the population. So sometimes you can write every single one of them down, and that's what you'd want to do. And sometimes you can't. You're going to describe the actual population. A simple random sample from a finite population, one in which every possible random sample size has the same probability of being selected. So if I have a group of 100 people and I'm taking 10, every possible group of 10 has the exact same percent chance of being selected. That would be a completely randomized sample. That's your goal. Whenever you're doing things, you want to try to get as close to a randomized sample as possible to deal with coming up with the information. All right. A biased sample would be one that overrepresents or underrepresents some segments of the population. We've talked about this. How would you get a biased sample? What are some ways that you can collect what would not be considered a random sample, which would be considered a biased sample? If you participate, yep, that actually would bias the sample. You should never participate in your own population or your own sample. What else? Any kind of survey, internet survey that things to do, would be a biased sample. Those are the ones we talked about before, because it's a self-selection or volunteering to do it instead of you randomly selecting people. So a couple different ones that are specific is a judgment sample. This is where, I can go back to it. It's just biased. There you go. A judgment sample is one where the expert chooses who they want to talk to. Because they're an expert in the field, they feel they understand where the data is coming from, and they pick the people they want to talk to. Why would that be a biased sample? Why would that be a bad thing?
Because it's not a true random. You don't get variety.
Imagine this. Trump was doing his own polling. It would say everybody loves him. Like that's literally like that would be like an expert in the field doing their own stuff. Or if a doctor is going out and has an interest in this medication doing well, they're going to pick people and stuff like that that's going to show it's doing well. All right. So a judgment sample is not typically a very good sample in that respect. A convenience sample will be a absolute or a representation of a convenience sample. If I wanted you to do a survey right now of all the students in Three Rivers, what would be the first thing that you'd come across of trying to find a sample? That would be a convenience sample. They're convenient. They're right here. All right, that's not a randomized sample. The other one we just talked about a little bit ago is that volunteer sampling. That's where you have those surveys and stuff like that, where you just ask people to volunteer to put the information down. Now, you might get good data. Who's typically going to volunteer to fill out a survey for you? Right, one way or the other. Okay, so like if I'm at a fair and we're going around and I'm asking, actually I went to one, we went to the Dragon Boat Festival last summer, and somebody was walking around with the clipboard asking questions, like asking how your day was and stuff like that at the event, and if you wanted more things and stuff. It's like the two people that are going to answer that survey are the people who absolutely hated it, or the people who loved it and want to see more. You're not going to get anything in the middle. And actually, you see a very similar thing in any type of review online. You see 5 stars and 1 star. You don't see very many 2 and 3 and 4 stars. That's why if you ever go to Amazon and looking for like reviews on a product, don't look at the 5s, don't look at the 1s, look at the 2, 3s, and 4s. They're the ones who actually really thought about it and have some good information for you. Okay? Because they're not the ones who are just like, oh, this is great, or oh, this sucks. All right? So that's where your volunteer sampling comes into play, and it's not a very good way to do it. Oh yeah, like figuring out like if it's good or not. Absolutely. You're going to get the same concept. Anybody who's like, and this is why the whole concept right now of like with Uber and stuff like that, where it's like, oh, you have to put 5 stars down and everything else, because otherwise it drops rankings. It dilutes the whole concept of the actual ratings. It's like, you might be good. It might have been a great ride, but you weren't perfect. So it's like 5 stars, and those things were designed to be a perfection. It's like perfect. That's what you'd want to aspire to be. Nobody's that way. There's always things you can do to improve. But the way things are now, you don't want to see that anymore. Which does cause a problem in our rating systems and our reviews and things like that. All right, so we have to be able to figure out a way to get a good random sample. One way is literally just simple random, where like I throw everybody into a computer and it spits me out 10 names. All right, or I have everybody choose random balls out of a bag and I'm choosing all the odd ones. Like that would be random. There are other ways to do it though. Because if I'm looking for, I want to do a survey for the entire United States. It would be very difficult for me to randomly select 5,000 people in the United States. It's going to take me a lot of time and effort and money to do that. So there's other ways to do it to maybe minimize that risk or that trouble. The first one is known as a systematic sample. This is where you put everybody in order and you take the 10th person, every 10th person. Okay. So if I have 3,000 people in the Three Rivers and I put all your ID numbers in order and I just circled every 10th one, I'd get a sample of 300 people. And that would be random because your ID numbers were kind of randomized. They weren't totally randomized, but they were kind of randomized. And that would give me a good sample. Even social security numbers and things like that aren't completely randomized. The first 5 numbers are actually depending on where you were born and when you were born. Like that's those first 5. The only random numbers are the last 4. All right, so let's say I wanted to do a survey in my town. And there's 947 blocks. Each one has 20 homes. So how many homes are in the town?
Wait, what was the cluster sample?
I'm going to talk about it right now.
Gotcha.
So how many homes are in this town? 947 blocks. Each block has 20 homes. One of those horrible subdivision towns. Believe it or not, like we don't see that very much here. But when you go out west, the towns that were like designed and built up, this is how they all are. So how many homes are in this town? Okay. And we want 300 of them. So if I wanted to randomly select 300 of them, I could put all their addresses in a list and select every 10th home, right? But now I'm going to send you guys out to collect the survey data. Those 300 houses out of those 18,000 are going to be spread all over the town, right? Is that going to be easy for you to be able to collect that information? If you have to run all over town to get it? No. So there's got to be better ways to do this. One of the methods is known as the cluster method. Instead of breaking up the town individually, we break up the town by groups. In this case, we're breaking them up into blocks. So I have 947 blocks. And instead of randomly selecting houses, I'm going to randomly select blocks. How many blocks would I have to select to get 300 homes? Each block has 20 homes. And I want 300 total. So how many blocks would I have to select? 15. I can send each of you to one block to collect the data. You'd walk around that block and get the data. Is that going to be easier for us to collect all that data than going all over the town to randomly to 300 homes? Yes. Okay. That's cluster sampling. Let's say the survey that I was doing was to put in a town pool. I'm collecting basically a petition to get a town pool put in at the local park. All right. You live in a town that has some wealthy areas, some poor areas, and some middle class areas. If I randomly selected 15 blocks out of this, do you think, so which groups of people would you think would be wanting a town pool? The middle and the lower class, right? The lower ones, because they don't have pools. So the upper class probably wouldn't want pools, right? Because they have their own. They're not going to go out and use them. They have their own. They don't really care. All right? Or they have one in their little HOA and they don't really need the town one. That's how I hate HOAs. Never. I do not understand why anybody would buy a place in an HOA. But so if I selected 30 blocks, I selected them randomly. I selected 15 blocks. I selected them randomly. 10 of those could be upper class blocks, right? We don't know. And that could skew my results. So cluster sampling works really well. And I'll go back and let you write down the actual definition. Cluster sampling works really well when the population is kind of homogeneous, like one type of group, okay? Where you split it up based on different groupings. Like if I was going to do the school, I can make the different groups be the classrooms. As long as all the classrooms have about the same number of people, I could just pick 10 classrooms and go around and collect data, and I could get that. That would be a random sampling, or a cluster sampling, I should say. So how would we want to deal with the fact that I have a group of people that are wealthy in my town, not so wealthy, and poor in my town? How would I go about doing a sample that took all those views into effect? How would you want to try to do that? Still doing the blocks. I still got 947 blocks. Could you tell which ones were wealthy beforehand, which ones were middle class, which ones were low? beforehand? Probably. You should be able to have that data. That's town data. You're probably you could probably literally just go by the actual value of the homes, right? The upper class is probably going to have homes that are worth a lot more money than the lower class ones. So what we'd want to do is, instead of just doing one cluster, we do what's known as stratified sampling. Stratified sampling breaks up those groups first. So let's say I have 947 total. See if I can do this and get the number right. I'll just use a calculator. I have 200 upper, 400 middle, and 347 lower. Okay, so those are based on blocks, not houses, just the blocks. So I have 200 upper class blocks, 400 middle class blocks, and 347 lower class blocks in my town. What percentage of the blocks is the upper class? How would I find that out? Now we have to do some math. Huh? How'd you get it? Yeah, so 200 divided by the 947. So it's like 21%. And if we did 400 divided by that, I get about 42%. 63, so that's about 37%. Right? So I'd want my 300 homes, or my 15 blocks that I'm going to pick, to match this percentage. So I'd want to pick about 3 upper class blocks, about 6 middle class blocks, and about, see, 6, 7, we're not 15, right? And about 6 lower class blocks. So now my blocks that I'm picking, I'm still going to randomly select 3 out of those 200, and 6 out of the 400, and 6 out of the 347. But now those blocks better represent the population of the entire town. Does that make sense? Huh? So if I just randomly selected 15 blocks, right? I could get all 15 in the 200 group. Because I'm just going to list all blocks and random, like throw darts and hit 15 of them. That's random. All right. The whole monkey picks random things, kind of the same thing. They could all pick out of the upper ones, I don't know. Or they could have all picked out of the lower one, I don't know. By using the stratified, I can break them up, and now I'm picking based on the percentage of that group for the whole thing. So since the upper is 21% of the entire population, I'm taking 21% of 15, which gives me the 3 blocks. So I'm going to take 6 of the middle ones and 6 of the lower ones, and you're rounding. It's not going to be exact. But as long as I'm getting 15 and no one's going to be completely over represented in that thing, the 3 of the 6 and the 6, that's pretty close to the better representation in that respect. Okay. So now I'd have a good random sample and still have the benefit of the cluster sampling. Yeah. So I still have the clusters. I'm just choosing a better way to choose out of my clusters. Okay. And you can break them up based on anything. Like we see this quite often in actual economic respect, but you could do it by sex, you could do it by political party, religion, anything, depending on which type of groups you're really looking at. Right? So remember I told you always answer the people with surveys and stuff? So I had Nelson Research called me the other day. They're doing a research study on allergies. And I go through and answer a bunch of questions. And then she goes, "Oh, I'm sorry. The group that you would have fit in is full," which is fine. I fill them up because honestly, they were going to do a 90-minute survey and give me $175. I'm like, that's great. I'll sit on a computer for 90 minutes talking to somebody, give me $175. But the group, so that's what they were looking at. They had a stratified group, and they were looking for groups of people to fill in those specific holes. Once they had enough people for that group, they don't need any more people for that group. Okay. So it works really well. It's just, again, everything that you want to do is you want to have a random sample, but you want to make it manageable. And we're talking about large samples, making it more manageable is a good thing. All right, I just covered 9.1 and 9.5. I'm about to cover 9.2 in a second. All right, any questions on random samples and stuff? And I literally had to pull the notes from chapter 1 from the previous book I did because that's where this stuff was. But I said I've already talked about a lot of this stuff. All right, chapter 2 or 9.2. There's only 4 questions in this section in Hawks, and it's literally the same question twice. When we're looking at doing sampling and trying to compare it to a population, you typically don't want to do just one sample. You want to do multiple samples. And the reason why is the more samples you do, the more data you get, then you can start to compare that information between hands. So the sampling distribution statistic basically states that the sample mean or sample proportion, we're going to look at both, is the probability distribution of all the values when you're looking at that sample. So remember how he said, or one of the questions on here was, on your test was, how many different ways can 3 phone calls be answered at the same time by 18 people? And it was like 280 something different ways. So to get all the samples, I'd have 286 different samples or 286 different groups. If I've done them all, the mean of those would be equal to the mean of my population. So if you can do all the actual samples, you're going to get a perfect representation of that mean. All right. Now, that's basically impossible for most situations. So we use the statistics and stuff like that to get as close as we possibly can to it. So your mean, so for example, the mean, that's your population, right? Your point estimator for this is that. That's your pop, and that's your sample. Okay? So the other ones, so there's 3 of them. So mean goes to that's the sample mean. We have, I think variance was just a V. Variance goes to that squared. Well, actually, no, it wasn't. It was standard deviation squared. Goes to that squared. And that goes to just S. Mean. Okay. Mean, these are the same thing. This is your population. That's your sample. Okay. We're never going to look at the population. We might be given information about the population. Most of the time, we're going to have sample data because it's impossible for us to get all the data from everybody. So we're going to have sample data. So most of the time, we're working over on this side. Okay, but we can use this information to find stuff on the other side. What was your question? You're good now? Kind of. We're going to do some actual problems with it. We're going to do some problems. Good, that's 9.2. Okay, so now we can go to the actual real stuff at 9.3 and 9.4, which is all the actual work. Yes.
the paper?
Yeah, because that's going to answer your 4 questions in Hawks on 9 too.
Question, what is it? So its mean is,
The bar with the X.
yeah.
Standard deviation squared is your variance.
Oh, that's variance?
Yeah, because remember, variance is just the square root of the standard deviation or
I
the
just
square.
figured out what the symbol was.
It's the standard deviation symbol. It's just squared, which is your standard deviation of your sample squared.
Oh, that's symbol.
Yeah, and then standard deviation is your standard deviation of your sample. They match. But that's actually all the question asks you is it says, what's the point estimate for the variance of a population? And you're just going to go, oh, it's this one. You pick that one out of the list of 4. That's literally all the questions for. So you should be able to do that with just that. In all honesty, not totally useful. So I'm not going into it a ton. 9.3 and 9.4 is where 99% of your stuff when you're doing statistics and which you really truly need to know, which is what I'm going to start now. All right. Unbiased estimators. Unbiased estimators means that they are not influenced by other things. So your sample mean is an unbiased estimator of your mean. Your sample proportion is an unbiased estimator of your proportion. Your sample variance is your unbiased estimator of your variance. Okay, so it basically goes back to what I was just showing you a second ago. I can use, these to estimate those, to get a good idea of what those really actually are. Okay. All right. This write down. This,
Supposed to write lots of it.
well, you can.
We need the last one.
Not as much as this one. This one you really are going to use a lot. All right.
I don't have my notes.
Just take a picture. This is why I post all my notes later. Because I can't make it much bigger.
We go back and get the notes versus.
Well, you also do a very good job of getting them down immediately. So, all right.
Go back.
There you go.
I don't do it now. It's never gonna happen.
So, remember what I told you you want for your samples. What size you want for your samples? If you're going to do the entire population, you're right. Around 1,200, you get a decent one for the whole population. But in typical, what was the size of your samples that you want to get?
1,000? No.
Anything over 30.
Oh.
So the number 30 is important because if it's over 30, that's when everything kind of falls into that normal bell curve. And we can use all the information that we learned about the bell curve. The z-table, the probability, and all that other stuff. And I lied, we might actually have to use the z-table, but that's okay. I'll throw it up on the board. So once it's over 30, we can start getting that information. Because of that, I can use certain things. The first thing is that the mean of those samples, okay, the sample mean equals the actual mean of the population. If I get them all. You're never going to get them all, but if I got them all, it would be exactly the same as the mean of the populations. Okay. And the standard deviation of the sample doesn't equal the standard deviation exactly. It equals the standard deviation divided by the square root of the number of values in my sample size. So what that is, actually got the nice, while you're copying that down, I'm going to get you a nice little picture to show you this. Really, let me in. It's me. Chrome added this biometric feature that actually it has to look for me now every time I ask for my passwords. Come on.
I'm so glad that the book they broke it down afterward, like they explained it in words.
Yeah. I'm gonna show you a little more to it. Once we start using them, things will make a lot more sense. All right. So, what does standard deviation tell us?
How many it is away from the median.
Right, how spread the data is, right? So if I was to do more and more samples or larger and larger samples, you'd expect the standard deviation to be smaller, right? Because it'll be closer to the mean of the actual population. The bigger the group I take, because if I took the entire population, it would be exactly that mean, right? There would be no variance. I'd have the exact number. So the more I do, the less variance that I'm going to have. Okay. So if I wanted to find the average age that comes to the Three Rivers, and I go through and I randomly select groups of 30. Okay. I might get a decent one. It might be kind of close, but it's going to be a little varied at that point. If I took and I did groups of 500, that's probably really close to what the actual mean is, right? If I was to look at those groups of 500. So my variance between them, because if I did more than one group of 500, is not going to be as much as if I did groups of 30. Does that make sense? Yes? Kind of? Okay. That's what that shows. The bigger the number, the skinnier it's going to be. Again, a lot of this will make sense once I actually do a problem with it. And you can see where it's used, which I believe is now. All right. A travel agency conducted a survey about prices charged by ocean ship cruise lines and determined that they were approximately normally distributed with a mean of $110 per day and a standard deviation of $20 per day. Okay. And I did lie, you are going to need your Z tables.
I love the travel agent.
Oh.
Looking at these numbers, I'm like, that's so horribly wrong.
Oh yeah.
It's so wrong.
It's way lower. It's way higher than what this is.
She has her own business answer. I don't want the woman.
I have 5 jobs. It's like the way the world works. Like
your friend wants to, like, their parent does one thing. In your head,
Yeah.
paying bills like their parent does
Yeah.
one thing.
All right. So, what is the probability that they will charge less than $99 a day? 0, I know. But in this situation, what is it? How would we do that? Think back to your test. This literally was a question very similar to what your test was. We got to find the z-score, right? So we find z-score by doing, so z equals the mean or the number which I wanted, was 99, minus 110 divided by 20. So I got a negative 11 over 20. Not that app. So I get negative 0.55. Let's look at our Z table. Thank you. I'll have it for you Tuesday. All right, so we're looking for negative 0.55. So negative 0, 0, 1, 2, 3, 4, 5.
Oh, sorry.
Yeah, I did.
I'm sorry.
I figured like otherwise I'd have to zoom out and you really can't read what it says. So 0, 1, 2, 3, 4, 5. So 0.29116. Yeah. All right. Now we wanted less than $99 a day, right? So is it that one or do I have to do one minus that? It's that one. Because remember, this goes from the left to that point. So this is already less than that. So that would be the probability that a randomly chosen person was charged less than $99 a day. Okay? That was exactly what you guys did on this test for a couple questions. Okay? All right. What's the probability that a sample of 35 people that the mean would be less than $99 a day? Okay, so now we want to look at, I'm picking 35 different people. So if the mean is $110, right? What do you think the odds of me picking 35 of them randomly and that average or mean is going to be $99 or less a day? Is that going to be bigger than 29.29116 or less than 0.29116? Yeah, it's going to be less, right? We'd expect it to be, the average should be around 110. The more I pick, the closer it's going to be to 110, right? So when we're looking at this, the only thing that changes in B is my standard deviation. So instead of it being just 20, it's 20 divided by the square root of 35. That's what that says. Okay? I take my standard deviation of the population divided by the number of the square root of the number of in my sample. So in this case, it's divided by the square root of 35. So I do 20 divided by the square root of 35. And I get 3.38.
Which number did that come from?
The 20 is still your standard deviation.
Very great. The equation, was that 1, 2, or 3 from the central limit?
It should be 3.
The 3.
Yeah, it was your standard
It
deviation
has
one.
the square root right
Yeah.
there.
That's basically what you're always going to be using. It's always going to be the square root divided by, or the standard deviation divided by the square root of whatever your sample was. In this case, it's 35 people I'm looking at. And I get 3.38. Okay? That step makes sense? That number is my standard deviation for a sample of that size. So your standard deviation of 20 is for individual people. The more people I take, now I'm making samples of groups. My standard deviation is not 20 anymore. My standard deviation is going to get smaller. Right. The standard deviation for a sample size of 35 is 3.38. Okay. And that would make sense. The more people you get, the closer it should be to that $110. There's going to be less variance in it. Now we're going to do the exact same thing I just did with A, except I'm going to use the 3.38. So my Z is 99 minus 110 divided by 3.38, or negative 11 over 3.38. And I get negative 3.25. All right, so if I look at my Z table and I go to negative 3.35 or 3.25, I get 0.00058. That would be the probability that I would get somebody, a group of 35 people, that the mean price would be less than $99 a day. Is basically non-existent. Does- Huh?
How did you know?
Because so the z-score needs two pieces of or three pieces of information, right? It needs the mean, it needs the sample mean, the one that the number you're looking for, and it needs the standard deviation. We had the mean, the population mean was 110. We have the mean that we're looking for, which is 99. We needed the standard deviation. That was that third formula. We actually used the second formula too, by the way. The second formula says the means are equal to each other. So I could still use 110. This one right here says 110 is both of them. This one here says my standard deviation is this now new formula. And that's where I got the 3.38 from. Does that make sense?
Yeah.
Okay. So this allows us to start looking at how unlikely something is to happen. Okay? Based on what we know. All right. So let's look at this one. So I'm going to find a few pieces of information, and then you guys are going to find the answers. So what's my mean? 75. So that is also my mean of my sample. Okay? Because those are equal to each other. That's what two, number two in that list of things said. My standard deviation is what? 12. My sample size is what? Yeah, they're all 50. So my sample size is 50. So what is my standard deviation of my sample? Yes, which is what? So it's 12 divided by the square root of 50. So I get 1.70. Well, the reason I need to find that is because now I'm using those samples to find the information for A, B, and C. Because now for A, B, and C, I need to find my z-score. So I need two pieces of information. I need my mean and my standard deviation for my samples. So that's my mean, and that's my standard deviation for my sample. No? It's fine. This is important. This is stuff that we're going to be using a lot. So we need to change this to this because that's for one person. That's for looking at 50 people at the same time. That's the difference. Okay. All right. So now you're just going to use your z-score formula. So it's the mean or the x minus the mean over the standard deviation. So find me A. Find the probability that the average of 50 scores is at least 80. Hey, if that's all that it took.
Yeah, right.
All right. So what's the z-score for A? Not the probability. What was the z-score? .94. About 2 places. Because your table is going to go for 2 places. So you always want 2 places. And now find that on the z table. Do I want the number that you get on the z table, or do I want 1 minus that number? Do I want the number you find in the z table for 2.94 or 1 minus it? I want 1 minus it because I want it greater than 80. It says at least 80, so I want greater than 80. So then I'm going to do 1 minus the number that's on. If it says 80 exactly, you can't do it. If it said less than 80, I would take that number. More than 80, because now I'm looking at the right side. I have to subtract. It's 1 minus. Because remember, the table's always going from left to right. If I want greater than 80, I want the piece over here. Okay? So that's why I'm doing 1 minus this whole piece. Because I want this little piece over here.
No, it's okay. It's okay.
No, it's fine. Draw a picture. You're fine. No, you're not. That's 80, right? I want this piece. The number you're finding is this piece. Why do you think she handed out little sticky notes last class? She handed out a bunch of they're during the review. You weren't here for the review. Yeah, during the review, she handed out little bell curve sticky notes because it literally helps you get. He has them. There you go. They're really they really are helpful because of this exact reason. All right, so my answer for this one's going to be, what was it, 94, right? Yeah. 0.00164.
Well, who found them and handed them out?
Michelle. Melissa, sorry. Yeah. All right. So here's the question. If that happens, all right, so I'm the person who runs these tests, not the one who gives them out, but the one who runs it. And I see a class for this one teacher. He came back and the average of his tests was above 80. Okay. So we had 50 students take this test. His average was above 80. What should I do? Am I happy? Or am I suspicious? Why? Because the chance of that happening is 0.164%. Not 1.64, 0.164%. Okay, so it's less than 1% chance. Actually, just about 0.1% chance of that happening. So if that happened, I'd be suspicious. Something went on. Cheating or something. Because that shouldn't have happened out of that one group of students.
You did this for your test?
Yeah. Honestly, the last 2 tests were easy. I will tell you that. The next test will not be as easy. I will tell you that much.
Well, that makes my dad feel really shaky.
But to be fair, the next test wasn't going to be that easy because this is the hardest material out of the whole group. Because it's kind of putting everything together. All right, but that's why this is important. Because we can start to look at if something is normal or not. We talk about like cancer clusters. That's what this goes with. If we start looking at a population and area has a cancer rate a lot higher than you'd expect in the normal population, that might be a problem. There's something environmental there that we might want to look at. Okay? So that's in essence what you're being able to start to do with this information. You can start to look at that and say, okay, this is unusual. Not just looking at the numbers, because like if forget this math, if I just said, oh, the class average was an 80, where normally the class average was a 75, you'd say, oh, okay, that's not that big of a deal. But now that we start to look at the statistics of it, that's actually a really big deal. That shouldn't happen. Okay? What's the chance, the probability that the average is less than 70? Yes. And do we want the number or subtract it from 1? Are we looking at the right side of the graph or the left side of the graph? We're looking at this piece. We want this piece over here, right? So we're fine. We would take that number. So that's the 70. So we're going to take that number, which ends up happening to be the exact same number that I got before. I did. And you get that same number. Because the number you would have gotten by looking at the table was 2.01234, 0.99836. 1 minus that gives you the 0.00164. Remember what I talked about symmetry? If you want to look at the opposite side, you can use the negative values. It'll give you the top side. That's what I did to get the 294. I didn't subtract from 1. I just looked symmetrically and looked at the negative side, and it gave me the same answer as if I was subtracting from 1. That's that whole how symmetry can help you look for one side. Both sides have to be the same. So in this case, if I had a class average that was less than a 70, I'd be just as suspicious as if I had a class average above an 80. Those would be equally suspicious. Something was wrong in both those situations. Okay. So anybody ever watched the movie Stand and Deliver? Nobody's ever seen the movie Stand and Deliver?
Wait.
Stand and Deliver was the Herman Escalante. He was the calculus teacher in Los Angeles that got his group of high school students to take the AP Calc exam. This was in an extremely poor, you would call it a ghetto area, and they passed and did very well in the AP Calc exam. And the College Board came in and claimed that they were cheating because his students did abnormally well. Yeah, did abnormally well on that test compared to what should have happened in an equally normalized group. And it was mostly because of the way he taught them. They did take it again. And they got actually a better score the second time they took it. And they, in the College Board, actually monitored the test. So, yeah. So they proved that they weren't cheating. But that's what they did. They looked, it was exactly this. They saw an average that was outside of that norm and said something's wrong.
Is that based on a true story?
Yeah, I actually met him. The professor, Herman Escalante. I can't remember the actress, the actual actor who did it. You have it there. But
Edward James.
oh yeah, Edward James Olmos did it. But yeah, Herman Escalante. When he said it was he didn't do anything like insanely like great. He had a group of students that was extremely motivated to do it. Those students came in before school, stayed late after school, came in on the weekends, came in on the summer. It is a true story. So these kids did a ton of work to prepare to take this test. It wasn't like he just took a random group of students and said, "Here, I'm going to teach calculus." They did great. These were kids. They were self-selected. They chose to do this. So, but he did take a group of students who never had the opportunity and gave them that opportunity, which was a very good thing. All right. So this is why we start to look at these groups, because the bigger the group, the smaller that standard deviation is, and then we can start seeing is something unusual. Okay. All right. So let me delete this slide and put a different one in here. We're going to do one more of these problems. I'm going to do one other one really quick because we talked about this before. Remember how we said they do inspections? They can't inspect every single item. They inspect groups of items to determine if they're going to reject or accept the shipment. Here's where we go. College Food Service buys frozen fish boxes labeled at 10 pounds. The true average weight of the boxes is 8 pounds with a standard deviation of 2 pounds. Right there, something's wrong, right? How are they labeled 10 pounds when the average weight isn't even 10 pounds? Okay, so he decides to inspect 40 boxes from the next shipment. If the average weight is less than 10 pounds, he's going to reject the entire shipment. As he should, exactly. So, what's the mean? My mean is 8. My standard deviation is 2. What's the standard deviation of my sample? No. Almost. It's not 8. It's 2. Over what? The square root of 40.
Oh man. No, my light's on, but I can't type. I want to go out or in.
All right, so 0.32 is my standard deviation. Okay, so now we've got to do my z-score, right? What's the x value that I want? 10. Minus the 8 divided by 0.32. That's my z-score. Is that z-score even show up on your chart? No. Is he ever going to accept the shipment? No. Okay. And as we said, he shouldn't. It's labeled as 10 pounds. It should be 10 pounds, not 8 pounds. Okay. So obviously with the 10 and stuff like this, and that one kind of throws it off. But that's where that important piece comes into play. It's like he's going to reject it because it's not coming out to where it should come out. Okay. All right. One more. No, I said I'm going to do one more of those, then I got to go on. Hey, I'm covering all of chapter 9 tonight. And I normally don't keep you late. I'm not keeping you that late. I got one more problem to do after this one. This is the formula. I got a problem to do. All right. So a lot of times when we're doing our work, we use proportions and probability for things. Okay. So it's either a binary choice. They liked it or they didn't like it, things like that. And we did some of these problems on your test, the binomial probability problems. This is similar to that. You'll notice that the mean is still the same. It's still whatever it's going to be whatever the probability is. It's whatever they're telling you the mean is, that's what the mean is going to be. Your standard deviation formula changes. It's actually similar to the standard deviation formula that we talked about in chapter 8. It's the p times 1 minus p. The only difference is we're now dividing it by the sample. Okay? So this formula right there, you don't really need to worry about that one. That's the formula you need. That's just the knots, which come out to be the exact same thing. Okay, so that's the formula we're going to use for this. All right, how many people like Pepsi? How many people like Coke? How many people don't care? Okay. No, it's fine. So if you were going to ask the entire population of the United States, what do you think the probability of people who would prefer Pepsi over Coke? It'd probably be pretty close to even, right? Like the same group of people. Believe it or not, it's actually, depending on where you are, but it's probably, they're basically the same, probably 50-50. Does anybody know the actual difference between the two? There's only one ingredient difference. Yes. Not anymore, unfortunately. So it would be a lot more addictive if there was. No, the actual only difference is citric acid. Pepsi has citric acid in it. That's what gives it a slightly different flavor than the Coke.
I wanted to say that, but I didn't.
Yeah. Coca-Cola really did have cocaine in it when it first came out. But it also wasn't a soda. It was a cough syrup and designed for colds, to take care of colds and stuff like that. And you actually can still buy cola syrup at the pharmacies for if you have a cough and stuff. It actually will soothe your throat and stuff.
Does it still have the
Yeah, I was like,
No. Does not have the cocaine in it. All right, so I'm doing a taste test. Yes, of 400 people, and to determine if the population prefers Pepsi is really 50-50. Okay, so what's my P or my mean that I'm looking at in the situation? 0.5. Okay. Now I want to find my standard deviation. I do them backwards. There's standard deviation. All right, what was the formula for standard deviation? That was the one you just had to write down or take a picture of.
Parentheses 1 minus p.
So 0.5 times 1 minus 0.5
Oh, yeah. And then
divided by the square root of, oh no, not the square root of, just 400. Because that was my n. So square root of,
why is that standard deviation?
that's the formula. P minus times 1 minus P over n. Yes. For these type of problems. For proportion problems. Ones that give you the probability. Notice that's the difference. This is a probability of that occurring, where this is like the actual weights. That's the difference between them. Yeah, it's very similar. The process and everything else after this is identical. It just depends on, since it's a probability problem. So that's my standard deviation. I think I did it right. Well, I did it on my calculator real quick, so. Yeah. And I didn't do it on the calculator that I can see exactly like it typed in right. So, all right. So what's my z-score? I'm looking for 0.44. So I did my taste test, and 44% of the people liked Pepsi. So what was my z-score formula? How am I going to set this one up? Same one we've used for everything. What number is going first? Yep. Minus, which is, yep, divided by, yep. So I get negative 2.4. So 0.00820. So that's the probability that less than 44% of the people sampled would prefer Pepsi. So if this is a sample that I did, and I'm assuming my work was correct, and I did a good random sample, and I got this answer, what can I conclude about the actual mean? Is it really 50-50, or is it less than that? Would you, if it was 50-50, would you expect this to happen when you did your study? No, because it's very slim, right? So if I did this and that's what I got, what assumption can I make about the actual mean? Is it really 50-50, or is it less than 50% likes Pepsi? It'd be less than 50% likes Pepsi. Okay. So that's where we can start to look at, we make an assumption about something. We're making the assumption that 50-50. We test, our test proves that that might not actually be accurate. Okay. So my population might be less than 50-50. It might be 45, 655, depending on that. Now, would I do this once and make that assumption? No. I would do it a few times. I'd repeat my sample, do it a couple times, and see if that's still what I get. And if I keep getting answers like that, then my assumption about my 50-50 would be incorrect. That's what we're going to start going into in the next couple lessons with hypothesis testing. We're going to make a prediction. We're then going to test that prediction using this to be able to show if it's correct or not. Okay? Don't forget these formulas, though. These formulas are going to have to be on your next card. I'm telling you that right now. You're going to use them a lot. All right. Yes, I have your tests. I handed them back at the beginning of class. You weren't here yet.
Yeah.
Name.
Rodolfo.
Was it?
Rodolfo.
There you are. If you didn't get your test, come get your test. Your grades are also in Hawks, but come get your test because I don't feel like carrying them around. It's not in Blackboard. I put it in Hawks. Names.
Mike. Thought we were on a first name basis.
I know, no, but I'm horrible with names. I really am. It's like my high school students, I wouldn't learn their names for months.
It doesn't help that I was seeing twice a week.
Yeah, that doesn't help. Yeah. There you go.
I'm here looking at my
See you next week.
Oh, put the lights off and I'm in bed asleep. I heard that. Like, the entire day has been, the lights have been going on and on. I can't decide if I want to go out or stay inside. Yeah. And I'm tired.
Okay.
Alright, so-
My high school students used to tell me, I fell off the bus. And then when they were really lost, they're like, you just ran me over with the bus.
Yeah, I'm just exhausted.
Name.
Like, I said, my mom said, I'm captain from the bus. So I crashed the bus into a tree.
It's not what I was planning to
and
do.
all the
There you
kids
go.
died.
Sorry.
I'm on fire. I'm